I am Subbalakshmi. We have discussed the dual behavior of an electron. Let us discuss Heisenberg's principle in this video. Let us consider any microscopic particle and its two parameters, position x and momentum p. According to Heisenberg, the more precisely one parameter is known, the less precisely the other is known. The more accurately we know about the one, the less accurately we know about the other. Or it is not possible to measure accurately both the position and momentum of an electron simultaneously. Heisenberg's principle can be mathematically represented as delta x into delta p is equal or greater than h by 2 pi. Delta x is the uncertainty in determining the position and delta p is the uncertainty in determining the momentum. Since p, the momentum, is equal to mv, m, the mass into velocity, then delta p is equal to m into delta v, where delta v is the uncertainty in determining the velocity. Therefore, Heisenberg's equation can be written as delta x into m delta v is equal or greater than h by 2 pi, where h is the Planck's constant and its value is 6.626 into 10 raised to the power of minus 34 joules second. To understand the Heisenberg's principle better, let us work out some problems. First problem, if an electron is located in an atom within a distance of 0.11 Armstrong units, what is the uncertainty in the velocity involved in the measurement? Heisenberg's equation is delta x, the uncertainty in position, into delta p, the uncertainty in momentum, is either equal or greater than h by 4 pi. But delta p is also equal to m into delta v, where delta v is the uncertainty in velocity, which we have to find out. So the equation can be substituting m into delta v for delta p and rewriting the equation, we get delta v is equal to h by 4 pi into m into delta x. We are following SI units. The value of Planck's constant is 6.626 into 10 raised to the power of minus 34 joules second or kilogram meter square per second. This we have discussed in one of our previous videos. Divided by 4 into the value of pi, that is 3.14, into the mass of the electron, that is to be taken in kilograms, 9.11 into 10 raised to the power of minus 31 kilograms, into delta x value. The data given in the problem is 0.11 Armstrong units. This is to be expressed in meters. 1 Armstrong unit is equal to 10 raised to the power of minus 10 meters. Therefore, delta x value is 0.11 into 10 raised to the power of minus 10 meters. To simplify, to solve the equation, we are separating the numerical parts and the exponential parts and working out. The numerical part is 6.626 divided by 4 into 3.14 into 9.11 into 0.11 gives rise to 6.626 divided by 1.259, and coming to the exponential part, there is 10 raised to the power of minus 34 in the numerator side, and in the denominator side 10 raised to the power of minus 31 into 10 raised to the power of minus 10 gives rise to 10 raised to the power of minus 41. On simplification of the units gives rise to meters per second on cancelling the common units, that is kilogram meter. So the simplified answer is 0.5267 into 10 raised to the power of 7 meters per second, and this can also be written as 5.267 into 10 raised to the power of 6 meters per second. That is, for a subatomic particle, that's an electron, the uncertainty in velocity is very, very large. That is 5.267 into 10 raised to the power of 6 meters per second for a very small uncertainty of 0.11 Armstrong units in position. Thus, the significance of Heisenberg's principle is well established here. Second problem. The speed of a moving ball of mass 150 grams is 40 meters per second. Its speed can be measured with an accuracy of 2%. What is the uncertainty in the position of the ball? M value is given in grams in the problem 150. On converting into kilograms we get 0.15. V the velocity is 40 meters per second. Delta V is the uncertainty in measuring the velocity, that is 2% of 40 meters per second, it comes to 0.8 meters per second. On substituting in the equation, the delta x is equal to h divided by 4 pi into m into delta v, we get 6.626 into 10 raised to the power of minus 34 kilogram meter squared per second divided by 4 into pi value 3.14 into m 0.15 kilogram into delta v, that is 0.8 meters per second. On simplifying the numerical part in the equation, that is 6.626 divided by 4 into 3.14 into 0.15 into 0.8, we get 6.626 divided by 1.5072. This on simplification gives 4.3962. Then the exponential part in the equation is 10 raised to the power of minus 34 present in the numerator side. And simplification of the units, that is on cancelling the common terms, we get meters. Therefore, the answer is 4.3962 into 10 raised to the power of minus 34 meter, which is the uncertainty in the position of the ball. The example taken in the second problem is a macroscopic object, a moving ball of mass 150 grams. For a reasonable uncertainty of 2% in its speed, the uncertainty in its position is in the range of 10 raised to the power of minus 34 meters, which is highly negligible. Therefore, we conclude that the effect of uncertainty principle is significant only for microscopic objects and it is negligible for macroscopic objects. Hope you find this video a useful one. Let us meet in the coming video.